In the beginning, before the concept of beginnings was even possible, there was nothing. Not a silent room, not a void waiting to be filled, but an absence more profound than any emptiness we can conjure. This is not the darkness of a moonless night, nor the hush of a sealed tomb, but a place, or rather, a no place where neither space, time, nor matter had meaning. The human mind recoils at such a prospect, for even our wildest metaphors strain and break when pressed against the edge of true nothingness. Yet it is from this formless potential that the universe, in all its majesty and terror, would one day emerge. Physicists reach for language, singularity, quantum foam, the absolute void, but each word only hints at a reality beyond comprehension. In this primal state, all the energy, all the matter, all the possibilities for law and chaos alike were curled into a seed infinitely smaller than the smallest known particle, a point so dense, so hot, so mathematically impossible that the very notion of measurement dissolves. This is the singularity, the enigmatic kernel from which everything would blossom. Then, roughly 13.8 billion years ago, something happened. Not an explosion, not a detonation in the emptiness, but a sudden, breathtaking expansion, a transformation of being itself. The Big Bang is a name both apt and misleading. There was no bang in the silence, for there was no silence. There was no pre-existing space to contain the explosion, no ticking clock to mark the moment. Space and time themselves were born in that instant, woven from the raw material of existence, shaped by laws that had previously lain dormant, unimagined, unneeded. In the first fraction of a second, so brief that our minds cannot grasp it, the universe was smaller than an atom, yet contained within it all the energy and possibility that would one day give rise to galaxies, stars, planets, and life. Temperatures soared past 1 billion degrees Kelvin, a heat so intense that the common-sense notion of temperature loses meaning. Under such conditions, matter and energy were interchangeable, ceaselessly transforming into one another, flickering in and out of existence in a quantum dance more intricate than any choreography ever staged. Particles and antiparticles burst into being, collided and annihilated each other, releasing energy in a ceaseless crackling storm. But by a fluke so improbable it borders on the miraculous. For every billion pairs that vanished, a single lonely particle of matter remained. This infinitesimal imbalance, an excess so slight it would seem trivial, ensured that matter would win, that the universe would not dissolve into a perfect bath of light, that stars and worlds and consciousness would one day emerge. The earliest moment of cosmic history is known as the Planck Epoch, a sliver of time just 10·43 seconds after the beginning. Within this epoch, the four fundamental forces of nature, gravity, electromagnetism, the strong and the weak nuclear forces, were united in an unimaginable synthesis. Physicists have spent lifetimes seeking to understand this unity, to glimpse the theory of everything that might describe the rules of creation itself. Yet, as we peer backward through the haze of mathematics and inference, the Planck epoch remains shrouded, its secrets protected by the limits of quantum gravity. Then came inflation, a period of expansion so rapid, so violent, that it beggars the imagination. Proposed by Alan Guth in 1980 and refined by André Linde and others, inflation posits that the universe expanded faster than the speed of light itself, ballooning from subatomic to cosmic scales in less than a blink. During this inflationary epoch, quantum fluctuations, tiny, random jitters at the smallest scales, were stretched across the cosmos, seeding the tiny imperfections that would one day become galaxies, clusters, and the cosmic web. When inflation ended, the universe continued to expand, but more sedately. Space cooled, energy dispersed, and the fundamental forces went their separate ways. Gravity broke off first, shaping the destiny of all things to come. The strong nuclear force next, binding quarks into protons and neutrons. Then, as temperatures continued to fall, the weak force and electromagnetism emerged, each taking up its role in the play of physics. In these first millionths of a second, the universe was a seething plasma, quarks and gluons racing freely, unbound by the familiar rules of chemistry. Soon, quarks began to pair up, forming protons and neutrons in a process called baryogenesis. The universe was still unimaginably hot and dense, but already the seeds of structure were being sown. 3 minutes after the beginning, The temperature had dropped enough for protons and neutrons to fuse, creating the first atomic nuclei. This era, known as Big Bang nucleosynthesis, produced vast quantities of hydrogen, a substantial measure of helium, and trace amounts of lithium and beryllium. These simple elements would become the building blocks for every molecule, every mineral, every living cell to follow. For the next 380,000 years, the universe remained a brilliant, blinding fog. Photons, the carriers of light, scattered endlessly off free electrons, unable to travel more than a minuscule distance before being absorbed or deflected. The universe was opaque, a churning sea of plasma, lit from within but shrouded to itself. But as expansion continued, as the firestorm cooled, electrons slowed and bound themselves to nuclei, forming the first neutral atoms. This epoch is known as recombination, though it was the first time atoms had ever existed. With electrons captured, photons were suddenly free to travel, racing outward in all directions. This ancient light is the cosmic microwave background, discovered by Arno Penzias and Robert Wilson in 1965 while investigating radio interference. It is the oldest light we can see, a snapshot of the universe as it was in its infancy, a relic that still bathes the cosmos in a faint, uniform glow. The cosmic microwave background is not perfectly smooth. It bears the faint imprint of those primordial quantum fluctuations, stretched by inflation into ripples in the density of matter. These ripples are the code from which all structure would grow. They are the reason we have galaxies, stars, planets, and, ultimately, the capacity to wonder at our own origins. After recombination, the universe entered a long, dark age. There were no stars, no galaxies, only vast clouds of hydrogen and helium drifting in the blackness. Gravity, patient and relentless, began to gather these gases into denser knots. Over hundreds of millions of years, these knots grew, compressing under their own weight, until the first stars ignited in a blaze of nuclear fusion. These primordial stars, known as population 3 stars, were titans, hundreds of times more massive than our sun, burning hot and dying young. They forged the first heavy elements in their cores, and when they exploded as supernovae, they scattered these elements across the cosmos. Every atom of carbon, oxygen, iron, and gold in your body was created in these ancient furnaces, the ashes of dead stars that lived and died billions of years before the Earth itself was born. The birth of stars marked the end of the cosmic dark ages. Their ultraviolet light tore apart the fog of neutral hydrogen, ionizing the universe and making it transparent to light once more. Galaxies assembled, clusters formed, and the large-scale structure of the universe, the cosmic web, began to take shape. Gravity sculpted filaments and voids, creating a tapestry of matter that stretches across billions of light years. Amid this grandeur, galaxies spun and merged. Stars were born and died. Black holes formed at the hearts of cosmic cities. The Milky Way, our home, began as a swirl of gas and dust, growing through countless collisions and mergers, its spiral arms unfurling in the darkness. The solar system, with its planets and moons, comets and asteroids, formed some 4.6 billion years ago from the remnants of earlier generations of stars. A cloud of gas and dust collapsed, spinning faster and flattening into a disk. At the center, the sun ignited, its nuclear fire sustained by the fusion of hydrogen into helium. Around it, particles of dust gathered into larger and larger clumps, coalescing into planets, moons, and smaller bodies. The Earth, at first a molten sphere, cooled and hardened. Volcanoes belched gases, forming an atmosphere. Water, delivered by comets and asteroids, pooled in low places, giving rise to oceans. In these ancient seas, chemistry became biology. Molecules assembled, grew, replicated, and evolved. Life, in its simplest form, began its grand experiment. Over billions of years, life diversified, adapted, and transformed the planet. From single-celled organisms to complex multicellular life, from the first fish to the rise of mammals, the story of life on Earth is inseparable from the story of the universe itself. For the atoms in our bodies were forged in stars. The water we drink is older than the sun, and the energy that fuels our thoughts was born in the first moments after the Big Bang. The universe, meanwhile, continued to expand. Edwin Hubble, in the 1920s, discovered that distant galaxies are moving away from us. their light stretched to longer, redder wavelengths by the expansion of space. This observation confirmed the predictions of general relativity, Albert Einstein's monumental theory, and helped establish the Big Bang as the leading model of cosmic origins. Yet, the universe is full of mysteries. Only about 5% of its content is made of ordinary matter, the kind that makes up stars, planets, and people. The rest is invisible, detectable only through its gravitational influence. Dark matter, first inferred by Fritz Zwicky in 1933, outweighs visible matter by a factor of 5. It binds galaxies together, sculpts the cosmic web, and remains stubbornly elusive, despite decades of searching for the particles that might compose it. An even greater mystery is dark energy, a force that pushes galaxies apart, accelerating the expansion of the universe. Discovered in 1998 by teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees, dark energy accounts for nearly 70% of the universe. Its true nature is unknown, a blank space in our understanding that challenges the very foundations of physics. Between these mysteries, the universe unfolds in patterns both familiar and strange. The cosmic microwave background, mapped in exquisite detail by satellites like COBE, WMAP, and Planck, shows tiny temperature fluctuations, 1 part in 100,000, that trace the seeds of all later structure. The distribution of galaxies, the clustering of clusters, the vast voids between them, all bear witness to the physics of the early universe. The laws of physics themselves, gravity, quantum mechanics, thermodynamics, arose from the conditions set in the Big Bang. They are universal, applying everywhere and everywhen, yet their constants appear finely tuned for the existence of complexity and perhaps of life. The ratio of the strength of gravity to electromagnetism, the mass of the proton, the charge of the electron. Small changes in these values would render the cosmos barren, unable to form stars or atoms or living beings. Some scientists like Stephen Hawking and Leonard Susskind have speculated that our universe is just one among countless others, a multiverse, each with its own laws and constants. In this view, the fine-tuning of our universe is not a miracle, but a consequence of cosmic selection. We exist in a universe compatible with life, because only such universes can give rise to beings capable of asking the question. Others, like Roger Penrose, imagine an eternal cycle of creation and destruction, universes born and dying in an endless procession. The tools we use to probe these questions are as remarkable as the cosmos they seek to unveil. Telescopes like Hubble and James Webb peer to the edge of the observable universe, capturing the faint light of galaxies billions of years old. Particle accelerators like the Large Hadron Collider recreate for a fleeting instant the energies of the early universe, smashing protons together at nearly the speed of light, searching for clues to the nature of matter and energy. Gravitational wave observatories, LIGO and Virgo, detect the ripples in space-time caused by the collisions of black holes and neutron stars, opening a new window on the most violent events in the cosmos. With each new discovery, new questions arise. The Hubble constant, the rate at which the universe expands, remains uncertain, measured differently by different methods, suggesting hidden physics or new ingredients in the cosmic recipe. The cosmic microwave background, so uniform, contains slight anomalies that may hint at exotic processes or worlds beyond our own. And the search for dark matter and dark energy continues, a quest as profound as any ever undertaken. Yet, for all our knowledge, the universe retains its mystery. The observable universe, the part we can see, is a sphere about 93 billion light-years in diameter, containing perhaps 2 trillion galaxies. But beyond that horizon, space may stretch on forever, or curve back on itself in ways we cannot imagine. The totality of creation may be far grander, stranger, and more beautiful than we dare to dream. From the largest scales, the cosmic web of galaxies, to the smallest, the quantum foam at the Planck length, the universe is a unity of opposites, order and chaos, simplicity and complexity, emptiness and fullness. Its laws permit both the regular ticking of atomic clocks and the wild unpredictability of quantum events. Its history is written in the language of mathematics, yet expressed in the poetry of starlight, nebulae, and the living world. Our own existence is both improbable and inevitable. The atoms in our bodies, the patterns of our thoughts, the spark of consciousness. All are products of cosmic evolution, shaped by chance and necessity, by the unfolding of laws set in motion at the dawn of time. To contemplate our origins is to glimpse the unity of all things, to see in the dance of galaxies and the pulse of neurons the same fire that blazed in the first moments of creation. Yet for all its grandeur, the universe is also fragile. The balance of matter and energy, the interplay of forces, the conditions that permit life, these are the result of cosmic accidents, the outcome of a history billions of years in the making. The Earth, our home, is a rare jewel, a blue oasis in a vast and often hostile cosmos. Its continued habitability depends on a delicate balance, a web of interactions as intricate as any cosmic tapestry. As we look outward, we also look inward. The search for understanding, the urge to know where we come from and where we are going, is as old as humanity itself. Ancient myths imagined worlds born from chaos, gods shaping order from the void, cosmic eggs hatching into creation. Today, our stories are written in the language of science, but the questions remain. What is the nature of reality? Why is there something rather than nothing? What will be the fate of the universe and our own place within it? The future of the universe is as mysterious as its past. Current evidence suggests that expansion will continue, perhaps forever, driven by the enigmatic force of dark energy. In trillions of years, the last stars will burn out, galaxies will drift apart, black holes will evaporate, and the cosmos may descend into a dark, cold emptiness, a heat death, where all energy is evenly spread and no structure remains. Or perhaps, as some theories suggest, the universe will collapse in a big crunch or fragment in a big rip, or be reborn in a new cycle. Yet, in the face of such vastness, our brief lives have meaning. We are the universe made conscious. The atoms of stars and the dust of galaxies come together to reflect on their own existence. Our questions, our dreams, our search for understanding, these are the legacy of 13.8 billion years of cosmic evolution. In the grand scheme, we are small, but our curiosity binds us to the stars. Consider the cosmic microwave background, that ancient light still glowing in every direction. Each time you tune an old television to static, a tiny fraction of that noise is the echo of the Big Bang, a signal from the dawn of time. When you gaze at the night sky, the light from distant stars has traveled for millions or billions of years, a message from a past so remote we can barely imagine. The story of the universe is not only written in the heavens, but in every atom of your body. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in the hearts of stars, scattered across space by supernovae, gathered into clouds, condensed into planets, and finally shaped into life. You are, quite literally, stardust contemplating the stars. In the laboratory, scientists recreate echoes of the early universe. At CERN, protons are accelerated to nearly the speed of light and smashed together, creating particles not seen since the universe was a fraction of a second old. At LIGO, physicists listen for the faint tremors of space-time, the aftershocks of black holes colliding billions of light-years away. In dark matter experiments buried deep underground, detectors wait for the faintest whisper of a particle that may never come. Each experiment is a window onto the past, a way of peering back through time to the moment of creation. Yet the answers we find are always provisional, always leading to new questions. The search is endless, but it is in the search that we find meaning. The universe is vast beyond comprehension. The Milky Way alone contains hundreds of billions of stars, each potentially surrounded by planets. Recent discoveries have revealed that planets are common, not rare, and that among the trillions of worlds, some may be habitable, some may even harbor life. The question of whether we are alone in the cosmos is one of the deepest and most profound we can ask. But even if life is rare, even if intelligence is rarer still, our existence is a testament to the power of cosmic evolution. From the chaos of the Big Bang, through the forging of elements in stars, the assembly of galaxies and the birth of planets, the universe has given rise to beings capable of reflection and wonder. The future holds both promise and peril. Our understanding of the cosmos grows ever deeper, yet the challenges we face, climate change, resource depletion, war, and division, remind us of our fragility. The universe will go on indifferent to our fate, but we have the power to shape our own destiny, to cherish the rare gift of consciousness, to explore, to create, to understand. In the end, the story of the universe is the story of connection. Every atom, every star, every planet, every person is part of a single unbroken chain, stretching back to the first moment of creation. We are the product of 13.8 billion years of evolution, the descendants of stars, the children of the cosmos. To contemplate the origins of the universe is to find humility and awe, to recognize our smallness and our greatness, to see ourselves not as isolated beings, but as part of a vast, interconnected whole. The questions we ask, the origin of matter, the fate of the stars, the possibility of other worlds, are the questions of the universe itself, whispered through us. As the universe expands, as galaxies drift apart, as stars burn and die, the legacy of the Big Bang endures. The cosmic microwave background, the distribution of galaxies, the abundance of elements, the laws of physics, all bear witness to the moment when nothing became everything, when silence became song, when chaos became cosmos. And so, as we gaze into the depths of space, as we ponder the mysteries of existence, as we search for meaning in a universe both beautiful and indifferent, we are fulfilling the deepest purpose of all. We are the universe, made conscious, striving to understand itself. Our questions, our wonder, our search for truth, these are the greatest gifts of all. The universe is not only out there, in the distant galaxies and ancient light. It is here, in the beating of your heart, the spark of your mind, the warmth of your breath. To know the cosmos is to know yourself, and to recognize in every star, every atom, every thought, the story of everything that ever was, and everything that ever will be. Thus, as the story continues, as new discoveries are made, as old mysteries are solved and new ones arise, the adventure goes on, the universe expands, the stars burn, life persists, and the quest for understanding never ends. In that endless search, we find our place, our purpose, and our home among the stars.